little bit in the 7.2. Seven point one is kind of the introduction to these inverse trig functions. 7.2 goes a little bit more in depth. And I want to rewind just a little bit and talk about this definition that I gave you last time, which is what the sine inverse function means. So, I'll write it right here. If you want to talk about this new function y equals sine inverse x, and remember the way we notate inverses with this -1 up here. The only thing you know about this new function, sine inverse, is that it comes from going to your usual sine function, which looks like this, and flipping the variables. X and y switch. Now I wanna talk a little bit about what this equation means to give you kind of a visual of what this function does. Here's original sine, actually. I'll write it in a different color. Purple is this color. Original sine. Right, so this equation is not the same as this equation, right? Because I switched the variables. Right, but here's original sine. What does this graph look like? How would you graph this if I begged you to?
Starts at the middle.
Starts at 0. And then it goes, so let me label these here. Pi over 2, pi, 3 pi over 2, 2 pi, and I'll go back a little bit because I don't know, it's fun. Negative pi, negative 3 pi over 2, negative 2. And then sine starts at a 0, goes to a max. What's the y value? 1. So 0, max, 0, min, 0. Something like this. And then in the other direction, it's going to follow the same pattern. It's going to go down, up to a 0, up to a max, down to a 0. So this is original y equals sine x. This equation, which is the same as the inverse function, right? The graph of this equation is going to be almost the same as the graph of the inverse function. Wow, what do you think this guy does to this graph? Any idea?
Reflects it.
Huh.
Maybe around the x-axis.
It's like a reflection, okay, but it switched completely the roles of x and y, completely. So everything that happens on the x-axis is now going to happen on the y-axis. So instead of splitting my x-axis up like this, with pi over 2 and pi, I'm going to do it to my y. There's pi over 2. There's pi. There's 3 pi over 2. There's 2 pi. And let me go down a little bit too. Here's negative pi over 2. Negative pi. Negative 3 pi over 2. Negative 2 pi. And then instead of having 1 and negative 1 on the y-axis, I'm going to have negative 1 and 1 on the x-axis. I'm still going to start, this is 0, 0 here. All right, 0, 0, pi over 2, 1. All of these are going to switch, right, because x and y switch. Pi, 0. These all switch. So 0, 0 will still be at 0, 0, but instead of being at pi over 2, 1, it'll be at 1 pi over 2. So imagine just tilting your head. That's all that happens. It ends up looking like this. Here's the top part. Okay? And then this part goes down. Like this. So this is the set of solutions. All of these points is the answer to this equation. What's the problem, though, with this graph?
It's not a function.
It's not a function. It's not even close to a function. Right, so just changing the x and y values gives you this mess. Right? which clearly fails the vertical line test because it hits this y-axis here, 1, 2, 3, 4, 5, and that's only in 2 periods. If you keep going, it's going to hit it forever. So what we did to fix that up is we said, okay, well, basically this guy needs to be between negative pi over 2 and pi over 2. If you're in this region, on the x-axis over here, back in the original sine function, you forget about all this, then you'll pass a horizontal line test, and therefore over here you'll pass a vertical line test. Over here, splitting these angles between negative pi over 2 and pi over 2 has the effect of splitting this graph between negative pi over 2 on the y-axis and positive pi over 2 on the y-axis. Which means that basically this stuff is ignored when you're talking about sine inverse. And just focusing on this little slice, we have a function. And it will do everything we need it to do. Which is why in this definition it says, in this equation, we need x to be between negative 1 and 1, and y to be between negative pi over 2 and pi over 2. In order for this inverse to be a function, this has to be true. Which is why over here, this box where my inverse is defined, right, this portion right here has y between negative pi over 2 and pi over 2. And it's got x between negative 1 and 1. So this is where the inverse function. Now solving, actually evaluating it is a little different story. When you're evaluating it, this is really what comes into play. You always need to make sure that the output of your inverse function is between negative pi over 2 and pi over 2. So usually I would write it like this. So if you ever get an answer when you're evaluating one of these that does not fit into this range, screw the pooch. It's wrong. Remember this, this x and y here represent, different things depending on where they are, right? I mean, this x and this y, because x is the input of an inverse trig function, right? Usually the input of a trig function is an angle. But if you look over here, the angle becomes the output. And the input to the inverse trig function is actually a ratio. And it's the thing you usually get out. So that helps if you keep that in mind when you're evaluating. So let's do our example. So I did A and B last time. I'll start at C. And if you don't remember A and B, you should pick it up once we do C. So part C here gives you that sine, it wants you to evaluate sine inverse of root 3 over 2. How does this work? What does this mean? What do you do? Mumble, mumble, mumble. Right, whenever you have sine inverse, you have to convert that to a regular sine equation. So sine inverse of root 3 over 2 is asking you, what angle do you take sine of to get root 3 over 2?
60 degrees.
Oh, I'm working hard.
Whoa.
Nobody cares about degrees.
Okay.
So, yeah, so you have to actually either look at a picture unit circle or have some kind of table memorized. Okay, but in my head, I have this picture floating around somewhere. Because I'm looking for where sine is root 3 over 2, I'm focusing on this y value right here, right? Because on the unit circle, sine is your y value. So this ray has a sine value of root 3 over 2, which means this angle right here will be my answer. What angle is that again? Pi over 3. So to solve an inverse, to evaluate an inverse function, you change it back to the original function, where this is what this is what the original function has to equal. This is the ratio. So then the answer would just be what do you think? Easy enough? How come, this is sort of where we left off last time, how come if I move to the second quadrant, which is going to have the same x and y values except with negatives on the x, so if I move to the second quadrant and I copy these x and y values down, but I put a negative on the x because I'm in the second quadrant, how come this answer over here, where the y is root 3 over 2, how come this isn't what I take for my sine inverse answer?
It's too big.
It's too big. More specifically, sine inverse, the angles always have to stay between negative pi over 2 and pi over 2. Here's negative pi over 2. Here's positive pi over 2. So between those means you have to stay in this portion of the unit circle. So once I pass that pi over 2 marker, can't be an answer to a sine inverse question. And if I go in the negative direction past the negative pi over 2, that doesn't work. Part D here, sine inverse, I threw in a negative sign. Negative sign, S-I-G-N. So, what does that do? How does that change things? So it doesn't change the original setup, right? Whenever you're doing a sine inverse, you are looking for an angle. Like this whole thing is an angle. What angle is it? It's the angle that makes sine negative root 3 over 2. So you go to your picture of the unit circle and you say, okay, what angle on here has a sine value of negative root 3 over 2? Well, these are all positive, so it's got to be down here. In fact, this guy, I still like this root 3 over 2, so let me copy him down. But I'll have to be in the fourth quadrant to get that negative out. Okay. So what's my answer here? Negative pi over 3. Right, if I go this way, down to a y value of negative root 3 over 2, I've traveled negative pi over 3. So that is the answer. But you have to be careful. What else is new? You have to be careful because, how do I put this? On most pictures of your unit circle, like if you have a printed out picture of a unit circle, this angle will be labeled 5 pi over 3. If I counted out around the unit circle, I would land at 5 pi over 3 here. If I went counterclockwise. So how come I'm putting negative pi over 3 as my answer and not 5 pi over 3? Because they're in the same quadrant, right? Negative pi over 3 and 5 pi over 3 are in the same quadrant. So what's the problem?
It's bigger than pi over 2.
Even though it's in the same quadrant, 5 pi over 3 goes around and passes this barrier here. Right? 5 pi over 3 is going to cross through the barrier twice. Okay, so it's bigger than pi over 2. That's why 5 pi over 3 won't work. 5 pi over 3 is not valid because it's bigger than pi over 2. Negative pi over 3 is okay. Right? That doesn't cross any barriers. So that's the one hang up with this. You gotta make sure you're outputting the right angle, in the right range. Sine inverse of 0. What? Crazy. Crazy. What is this guy doing? So this is an angle, right? Sine inverse is always an angle. And what angle it is depends on the original sine equation. So you have to solve the equation sine of theta equals 0. So the question becomes, where on your unit circle do you have a sine value of 0?
Pi negative 0.
0. Remember, sine is your y value. So here, y is 0, x is 1. Here, x is 0, y is 1. Oh, did I? Y is 0, x is 1. Right, so these have a 0x value, which doesn't matter. This has a 0y value, which is what we care about for sine. Now, this also has a 0y value. And this ray right here, the ray that lands on the positive x-axis, has a lot of names. It can be called 0 radians. It can be called 2 pi radians. It can be called 4 pi radians. This ray over here can be called pi radians, 3 pi radians. And both of these have a 0y coordinate. They have a 0 sine value. So then why am I going to pick this as my answer?
Because it's too big.
It's the only one that falls in this range between negative pi over 2 and pi over 2. Right? If you pick any other one, you're going to have to pass your barriers. If you go 2 pi, then you have to pass both of these barriers. If you go pi, you have to pass this barrier. So the only answer that's going to be in the correct range is if theta, if the angle is 0 radians. So the answer to this is 0. Sine inverse of 0 equals 0. Oh, we just did E. I meant F then. One of those letters. This is sine inverse of negative 1.
Negative pi over 2.
Correct. Sine inverse of negative 1 is asking you for the angle that makes sine equal to negative 1. So you're looking for where your sine value is negative 1, it's got to be down here. Okay? And you can't go 3 pi over 2, you can't go this way because you cross your barrier. So you've got to go this way. Which means that this is negative pi over 2. Good enough? Okay. So then we need to do inverse cosine inverse tan. So again, let me first talk about what regular cosine and regular tangent look like. So y equals cos x. What's this guy do? Starts in max. Let me go and label my x-axis here. Pi over 2, pi, 3 pi over 2, 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Cosine starts at a max, which is at 1. Goes max, 0, min, 0, max. And then backward it goes 0, min, 0, max. Again, this fails the horizontal line test, so it won't have an inverse function as it is. But if we restrict our domain, we can then flip it and get our inverse function. So what do you think the restricted domain should be here? Right, if you look at the same x values, negative pi over 2 to pi over 2, if you look at this region here, you don't pass the horizontal line test still. Yeah, so you could try 0 to pi instead. That might be easy. So if you do 0 and pi, we do, and you ignore all of this garbage, and this portion of the graph definitely passes the horizontal line test. So basically what that's going to do so you have a picture in your head here. Negative 1, 1, pi over 2, pi, 3 pi over 2, 2 pi. The normal cosine graph, if we switch everything around and we do x equals cos y like before, if we just switch the variables, that'll just switch what happens to the x and y coordinates here. So you'll go max on the x-axis, 0, min, 0, max. 0, min, 0, max. So it looks like this. Like that. But again, this is not a function, so we've cut off our angles between 0 and pi. We only care about this box here. All of this is useless for inverse cosine. This would be y equals cos inverse of x. Right, and that's what the definition says down there at the end. Cos inverse of x means x equals cos y. It means solve this equation, but you have to have x between negative 1 and 1 and y between 0 and pi. These equations mean the same thing as long as x is between negative 1 and 1 and y is between 0 and pi. So it'll be exactly the same when you're calculating, when you're evaluating cos inverse, but you just have to make sure you get answers between 0 and pi instead of between negative pi over 2 and pi over 2. It's the main difference between cos inverse and sine inverse. You have a new output range. What about tangent? What's tangent look like? Snake, for lack of a better word, I guess. What about asymptotes? For the original tangent graph, where are my asymptotes? Negative pi over 2 and positive pi. So the way tangent works, it's got asymptotes at negative pi over 2 and positive pi over 2. That's a snake. As far as the restricted domain goes, I passed the horizontal line test here. Right? Now if I start drawing the next period of tangent over here, then I'm going to have a problem because this won't pass the horizontal line test anymore. But if I just focus on this fundamental period, on the usual period we draw of tangent x, and ignore all the other periods, I will pass the horizontal line. So for tan x, this is where we restrict our domain. Negative pi over 2 to pi over 2. So we focus on this portion. On this portion. And what do you think that's going to do to the graph of v? Right, if we switch x and y here, what happens? What's the graph look like? Any idea? Sideways snake, right? So if you switch x and y, and you want to talk about the equation x equals tan y instead, which is what the inverse function is going to do, then these vertical asymptotes are going to become horizontal asymptotes, right? Because everything about x switches to y. So I will have horizontal asymptote at pi over 2. Horizontal asymptote down here. This 0, 0 will flip and stay 0, 0. Something like, can you give me a point on the tangent graph that's right here, right in the middle at a quarter period? Pi over 4 comma 1. That's going to go to 1 comma pi over 4. X and y switch. This is your inverse tangent graph, or your x equals tan y graph. Horizontal asymptotes instead of vertical asymptotes. And if I wanted to make this one not a function, kind of like how this was not a function, I would have to keep graphing the next period, which would be a horizontal snake up here, or horizontal snake down here. But as long as I stay between these two y values, I should be okay with the tangent inverse. So if you look down here, for tangent inverse, that's the same thing as x equals tan y, as switching the x and y in the tangent graph. And the only restriction is that y is between negative pi over 2 and pi over 2. Why is there no x? Why do you think there's no x restriction? Look at the picture. X goes on forever. X goes on forever here. Because y goes on forever in the original. So for the tan inverse, this is the only thing you have to worry about. And this is kind of nice because pi over 2 and negative pi over 2 are the same numbers that you use when you're evaluating sine inverse. So tangent inverse and sine inverse have almost the same range, almost the same angle values. What's the difference, though, between tan inverse and sine inverse, as far as these pi over 2s go? Right, tangent can't be equal. Tan inverse cannot ever equal pi over 2, because it never actually makes it to this asymptote. But that's technicality at this point. So let's do some problems. Find the exact value of each expression. A cos inverse of root 2 over 2. What do you think that is? Pi over 4. It's got to be pi over 4. But what's the logic? How do you know? What do you solve to get pi over 4? An inverse function is always asking you for an angle, right? This whole thing is an angle. What angle is it? It's the angle that makes cosine root 2 over 2. So what angle is it? It's the angle that makes cosine root 2 over 2. So then you turn to your handy-dandy unit circle. You know root 2 over 2 is here. Because it's cos inverse, we're looking for an x value or a y value here. X value, cos inverse is going to look for an x value of root 2 over 2. So this is your reasoning for why cos inverse of root 2 over 2 is pi over 4. Okay. So it's the same exact logic as sine inverse, except you do it with cosine, you do it with the x side. You have to be able to. So cos part b there gives you cos inverse of negative root 3 over 2. That was a pretty good vibration impression. I pride myself on that. That's what I was going to do for a living. I was going to imitate vibrating phones, but stop it. There's no need for that. So how would we do cos inverse of negative root 3 over 2? What do we solve? What do we think? Where is cosine? What angle makes cosine equal to negative root 3 over 2? Right? This is what you want to do. But you have to be slightly careful here only because the first quadrant doesn't work. Right? In the first quadrant, cosine root 3 over 2 on pi over 6 ray. But I need cosine to be negative root 3 over 2. Okay? So then I either have to be in the second or third quadrant for cosine to be negative. Right? Cosine's the x value. Negative x values are over here. So in the second quadrant, this guy's negative root 3 over 2, 1/2. So this satisfies my equation. This guy is going to have a cosine value of negative root 3 over 2. So this is my ray. What angle is that? 5 pi over 6. But wait, you say, Josh, upset at me for some reason? You passed this marker here. You went past pi over 2. That can't work. Do we care? That was for sine inverse. Right? For cosine inverse doesn't give a crap about pi over 2. Cosine inverse cares about 0 and pi. So if you ever pass one of these barriers, then you're in trouble for cosine inverse. But pi over 2 is irrelevant for cosine. So 5 pi over 6 is a perfectly legit answer because it hasn't passed either of these purple rays.
And what were the barriers for tangent again?
Pi over 2 and negative pi over 2, they're the same sign.
Where do we get the proof that we have to stay between 0 and pi?
We chose that. Remember when we graphed cosine,
Oh, right.
we had to restrict our
Yeah, I
domain.
remember now. That's where we put the lines.
Yeah, we had this part and we restricted. Now be
It's
careful.
0 pi.
Right, so 0 to pi gave us a good restriction because we passed the horizontal line test on that interval. But you can choose other intervals if you really wanted to, right? This isn't the only interval where cosine inverse can be defined. You could choose if you wanted to pi to 2 pi. And everything would work the same because you pass the horizontal line test there. But no one would ever do that because 0 to pi is easier, right? I mean, the numbers are smaller. It includes 0. Right? So this is kind of the usual choice for where we restrict cosine. Last one here. Tan inverse of negative root 3 over 3. Negative? So whenever you do an inverse function, this is going to give you out some angle, right? Some angle theta. And we just need to solve the equation tan theta equals negative root 3 over 3. Right? We need to figure out where regular tangent is equal to this number. It helps on these problems to have your tangent values memorized so you don't have to do a bunch of annoying calculations. Right, in the first quadrant, these are your x and y values. Hopefully you have these down by now. So there's your x, y values. But tangent, you have to do y over x. Right? Tangent is always y over x. But you only get so many answers here, right? When you do y over x here, you'll get root 3 over 3. When you do it here, you'll get 1. When you do it here, you get root 3. So the tangent values increase around the unit circle. It starts with a fraction, then it goes to 1, then it goes to a number bigger than 1. So this is almost good, right? Because I want tangent of theta equal to negative root 3 over 3. So I have positive root 3 over 3. What do you think I'm going to have to do to make this negative? Which way do I want to go? Keep going this way? Let's go down. So if I go down into the fourth quadrant, tangent will be negative root 3 over 3 here. Which means I'm looking at this angle, which is negative pi over 6.
Why would you go down? Wouldn't it be the same in the other quadrant? If you went like...
Whoa, blowing my mind. Blowing my mind. What are my barriers for tan inverse?
Oh, that's right. Pi.
Negative, yeah, not 0 pi, but negative pi over 2 and pi over 2.
I'm still thinking of cosine.
Gotcha. So for tan inverse, these are your barriers again. Just stay. Just stay with me. The cool thing is, I mean, for sine and cosine, it's kind of obvious where the barriers are, right? Because sine is always your y value. So the barriers for sine inverse are the y-axis. Right? This is where sine inverse is defined. Cosine is always your x value. Right? The barriers for cos inverse are your x-axis. So cosine inverse is always defined in these, between 0 and pi. And then tangent you can just tag on to sine. So both sine inverse and tan inverse are between negative pi over 2 and pi over 2, which are y values, or on the y-axis. Cos inverse is 0 to pi. What do you think, team? So far, so good? It's going to get a little tricky now. A little bit tricky. So the whole point of inverse trig functions is to help us solve trig equations. Okay, I would like to be able to take this trig equation I'm going to randomly make up. Sine of theta equals, I don't know, 0.27. I would like to be able to take this trig equation and solve for theta. Right? If this is one of our special ratios, like root 2 over 2, then we can do it in our head. Right? In order for sine of theta to equal root 2 over 2, theta has to be power 4. But if this isn't a special trig ratio, I would like to be able to use my inverse trig function to solve this. And the way you would solve this using your inverse trig function is you take sine inverse of both sides. On this side, hopefully, sine inverse of sine cancels, they undo each other, and leaves you with theta. So what we would like to say is that these cancel and leave you with just theta. So we would end up with theta equals sine inverse of 0.27. thousands of mathematicians over the years have found a nice way to approximate sine inverse and then programmed it into your calculator, and now you can do this with a calculator. But what I'm interested in is when is this true? Is this always true? And that's what the next part of the notes kind of goes into. This is where I believe 7.1 and 7.2 split. 7.1 is just the basics, making sure you understand sine inverse, cosine inverse. But then as we move on, we want to be able to mix them. Right? We want to be able to do sine of sine inverse, or cos of sine inverse, or tan of cos inverse. Right? We want to be able to mix our regular trig functions and our inverse trig functions. So first we talk about what happens if you mix the same two trig functions, but one inverse and one not. Right? So the question up there under the remark is, does sine of sine inverse of x always equal x? Is this always true? And so this is the big question, at least for the moment. And does sine inverse of sine of x always equal x? So if I change the order, it is always equal. Well, let's think about this. What does sine inverse take as an input? What do you have to plug into sine inverse? An angle or a ratio? Ratio. So this x in this equation represents a ratio. You plug it into sine inverse first as a ratio. Then sine does something, right? Sine inverse does something, and then sine does something, and then it spits out again another ratio. And the question is, are these two quantities always equal?
Yes. Well, maybe not always, but they should be.
Maybe not always, right? So when aren't they, or what could go wrong here? So this goes all the way back to the definition of sine inverse. What do you have to have? Let me go back here. Right here. Sine inverse. What has to be true about the x value? Between -1 and 1. It's a ratio. So in order for this to make sense, x has to be between -1 and 1. It will. It'll be perfect. It will make perfect sense. The equation will be true. Right? This equation is true. As long as x is between -1 and 1 for ratios that make sense. Meaning, for example, if I write sine of sine inverse of 2 equals 2, it's garbage. Doesn't make any sense. You can't do sine inverse of 2. It's meaningless. So you're saying meaningless equals 2. Okay? Doesn't make any sense. But if you put anything less than 1 or bigger than -1 in there, this will be fine. So I can say sine of sine inverse of 0.27 is equal to 0.27. That's true because this is between -1. It makes sense to put this in the sine inverse. Okay. Okay. What about here? What is x? Let's do the same analysis. Here, x was a ratio because I was feeding it to sine inverse. Here, what's x represent?
An angle.
An angle, two people say. Good, that's better than 0. How do I know it's an angle? Because it's going into sine. Sine always takes in an angle. So these guys here represent angles. More importantly, this angle is coming at the end of the day from sine inverse. Right? If you put a number in here like pi over 4, then you do sine of pi over 4 first, and then sine inverse of pi over 4 after that, and that gives you your answer. So this is coming from sine inverse.
It can't be greater than 1 or less than 1.
I don't care about 1 for angles. What's important for angles? Yes, pi over 2s are important for angles. So up here, I'm actually focusing on this y, even though it's not y in the equation I wrote. I can make it y. So I need my angles to be between negative pi over 2 and pi over 2. Then, as long as I'm in that range, I'm okay. Then this will be true. If I'm not in that range, I can still make sense of this equation. I can still make sense of this composition, but it won't equal x. Right? I'll show you one of those. If you scroll down here. So here's some examples. I'm going to show you one where, see, let's take this guy for example. Even though we're outside of the range, right, this is 2 pi over 3, which is bigger than pi over 2, I'm still going to be able to get an answer out of this. Still get answers out of this, it just won't be equal to x again. By the way, what do you think happens for tan and tan inverse, right, and cosine inverse? Like, what if I change this to cosine inverse of cosine of x, and I want to know when that equals x? What do you think has to be true about x? Right. You go to the cosine inverse definition. And this is true for x between 0 and pi. What about tan? Tan inverse of tan of x equals x. This is true for negative pi over 2 to pi over 2. Right? Because remember, tangent matches up with sine. Tan inverse matches up with sine. Only works in. Find the exact value of each expression. Sine inverse of sine of pi over 3. Now for this one, there's two ways I can do this. One way is to trust and believe in logic. And say that if I want to take sine inverse of sine, right here, of an angle, that's going to be equal to the exact same thing as long as you're between 0 and pi, or negative pi over 2 and pi over 2. So is this guy between negative pi over 2 and pi over 2?
Yes.
Right, so pi over 3 is between negative pi over 2 and pi over 2. Because it fits in there, you can actually say this is equal to pi over 3 dot. They cancel in this case. It's kind of upshot. But maybe you don't believe, right? Maybe you're a non-believer. The world is filled with them. That's okay. Because you can do this the long way, right? You actually know what sine of pi over 3 is. You can actually calculate this. And then once you know what that is, you can plug it into sine inverse and calculate that. And see what you get. And I like to do that because it's going to help us with part B. So if I were going to figure out, calculate somehow what sine of pi over 3 equals, what would I do? Yeah, you can use your special triangle or unit circle. Right, but you go to pi over 3. 1, 2, 3, which is out here. This is 1/2 root 3 over 2. So sine of pi over 3 is equal to what? Root 3 over 2. It's the y value here. So this guy is equal to root 3 over 2. Which means I can then go in and calculate. I haven't done the sine inverse yet, but I can replace sine pi over 3 with root 3 over 2. So now I go in and calculate what's sine inverse of root 3 over 2. So then you look on your unit circle for where your y value is pi, or for where your y value is root 3 over 2. and you get your angle of pi over 3. So it gets you right back where you started. Now this probably seems like a lot of hullabaloo, a real word, for getting an answer we already got. But let's look at part B here. Not in blue. Oh, B for black. B. Let's look at part B here, which says sine inverse of sine of 2 pi over 3. What happens here? Can I just cancel these out and say my answer is 2 pi over 3? No, because it's not in the right range. Right? It's not between pi over 2 and negative pi over 2. 2 pi over 3 is way over here. And it passes our barrier. Here's pi over 2. Here's negative pi over 2. 2 pi over 3 goes through a barrier. So that means these aren't going to cancel exactly. Okay, fine. Life sucks. Move on. What we have to do then is we have to calculate it this way. We have to figure out what sine of 2 pi over 3 is first. So sine of 2 pi over 3 will be up here in the second quadrant at the point negative 1/2 root 3 over 2. That's the xy value for 2 pi over 3 angle. So sine of 2 pi over 3 is equal to root 3 over 2. Which means we now have to calculate sine inverse of root 3 over 2. What's sine inverse of root 3 over 2? Is it 2 pi over 3? Do I pick this guy here? No, this guy went past my barrier. I cannot use this angle as an answer to sine inverse. So I have to be over here. I have to be in this range. So I move to this angle. And I see, oh, I have another root 3 over 2 sitting right here. But that one's at positive pi over 3. Positive 1 pi over 3. So instead of getting out 2 pi over 3, we actually got out single pi over 3. So the sine inverse is always going to, this sine inverse that you do at the end is always going to push you back into this range. That's where you always output for sine inverse. Ooh. Doo, doo, doo. So like this guy, sine inverse of sine of 5 pi over 19. What say you trig students? What's your debate? 5 pi over 19, why?
Between pi over 2.
Yeah, this is in the correct range. Right? If you graph this, here's pi over 2. Here's negative pi over 2. Here's 5 pi over 19, somewhere down here. How do I know this hasn't gone past pi over 2? Yeah, you would have to get the top to be half of 19 in order to get pi over 2. Right, so half of 19 is what, 9.5, 9.5? So as long as the top is less than 9.5, this whole fraction is less than pi over 2. Which means it's in the correct quadrant, so we can answer this very easily. I'm going to give you one that's not up there because I don't think we'll know how to do it. This is great, right? As long as it's in this range, everything is squeaky clean. Right? As long as you're between negative pi over 2 and pi over 2, it just pops right out. If it's not between negative pi over 2 and pi over 2, you can do it the long way where you calculate it. But what if it's incalculable? Okay. So extra example, let's part C and a half. Sine inverse of sine of, oh, let's do 17 pi over 19. Where does this land? Second quadrant, right? It's not quite 19 pi over 19, which would be pi. It's a little bit less. Here's 17 pi over 19 hanging out over here. Maybe a little bit less than this. Yes. Now, it's past my barrier. Right? It's gone past pi over 2. So I don't know what sine equals here, but I know this angle is too big to get out as an answer when I do sine inverse. So what do you think is going to happen? Right, I calculate sine of 17 pi over 19, I get out y, whatever this ratio is here. What do you think is going to happen when I do sine inverse of that? It's going to push it back. Right, just like it did here, it took 2 pi over 3, and at the end of the day we pushed back to pi over 3. We pushed back into the range that sine inverse likes. So 17 pi over 19 is going to get pushed back here, right, because, say this is a negative x and a y, right, because it's in the second quadrant, so x is negative. Well, in the first quadrant, it'll be a positive x and a y. And the whole question is, what's this angle here?
2 pi over 19.
Yes, why?
Is this the difference on the other side?
Yeah, look, it's a mirror image here. This guy had another 2 pi over 19 to go. So this guy has 2 pi over 19 to go to get up the same y. So these sine inverses, usually they can cancel. At least sine inverse and sine can cancel if you're in the right range. Okay? Sometimes they can't cancel, but you can calculate it using your special angles. Sometimes they can't cancel, and you can't really calculate it using a special angle, but you can use a little bit of rationale to see that the sine inverse is going to push this angle back into the first quadrant. So the answer here is going to be 2 pi. Oh my God.
So, to find the sine inverse, you just need to like complete the whatever pi over 19. Just complete the other side, like.
Yeah, you have to figure out an angle that has the same y value, so an angle that's basically the same height, but in the first quadrant. So you kind of reflect it over always for sine. Okay. Let me finish these up, and then we can go, and I can review this a little bit on Wednesday. I didn't like this one. But let me go back to the planned examples here. So sine of sine inverse is 0.99. What's changed between one of these examples and one of these examples? The order, right? The order's changed. Now the inverse is on the inside. Okay. Well, if the inverse is on the inside, that means this isn't an angle anymore. It's a ratio. And for ratios, we want to be between what and what? Negative 1 and 1. Is this between negative 1 and 1? Sweet. Because this is between negative 1 and 1, we can just cancel them and get out the same ratio that we started with. Right, we need this ratio to be between negative 1 and it is. So then what do you think happens with e here? Sine of sine inverse of 1.01. So can we do a fix-up like we had here? Where it pushes things back? And no, because this doesn't even make sense. Right? In example B here, where we had 2 pi over 3, we could fix this because sine of 2 pi over 3 still made sense. But sine inverse of 1.01, there's no, it just blows my mind. This is undefined. Oh, that's kind of mean, but I'm a mean guy. Depends on when you catch me. Sine inverse of sine of 1.01.
Now it'll be like the other one, right?
So now it'll be like this one because the sine inverse and the sine are flipped. So because the sine is back on the inside, this is an angle. And in order for this to cancel, the angle has to be between what and what? Pi over 2 and negative pi over 2. So the question becomes, is this between pi over 2 and negative pi over 2? Why? No, it's in radians. But give me an approximation here. What's pi approximately? 3.14. So 3.14 over 2 is 1.57. So pi over 2 is approximately 1.57. Is this less than 1.57? Then we're good. This is in the correct range. So these will cancel. All right, why didn't I worry about that here? Because 1.1 is not an angle here. 1.1 is a ratio. And as a ratio, it makes no sense. Okay. Yes, go ahead.
So when you graph, like for example, D, do you just like decimate?
Do you? Oh, you mean like I'm in a circle like this?
Yeah.
So if I were to draw a graph here, I would need to know, right, what does this 0.99 mean? It's a ratio. So I would have to have the y value equal to 0.99. So it would be up here if I graphed it. And so this is where your y value equals 0.99. So you're looking for this angle or this angle. But there's no need. There's no need. In this order, it's either going to be less than 1 and then it works, or it's going to be greater than 1 and then it doesn't. There's no need for this kind of tricky business.
If f is in radians, wouldn't it be 1.01 pi?
No, you don't have to have a pi to be in radians. It just usually is.
So then wouldn't it be past pi 1 and then it would actually...
What? Wouldn't it be what?
It would be past pi then by 0.01, right?
No, this doesn't have pi attached. If I wrote this, you'd be right. But this is not the same as this.